Hello everyone, welcome back to yet another video on Thevenin's and Norton's theorem. In previous video, I had explained that how to obtain the Thevenin's and Norton's equivalent when we have dependent sources in the circuit. This is the extension of that video only. In this video, I will solve three more problems so that you can understand it better that how to solve the problems when we have dependent sources. Now the question which I am taking as first problem is find the current through 9 ohm resistor using Thevenin's theorem. Now, the circuit is consisting of a dependent source and an independent source. Both are voltage sources. This is 9 ohm resistance is actually load resistance. This resistance value is 6 ohm. This voltage source is supplying voltage 6 times Ix, and Ix is the current through this 6 ohm resistance. This resistance has value 4 ohm and this voltage source supplies 20 volts. So this is a current dependent voltage source and controlling quantity is Ix. Since we have a dependent source in the circuit, so it's not possible to calculate RTH by removing the sources. We need to find out RTH by taking the ratio of open circuit voltage to short circuit current. So first step here is find open circuit voltage. For finding open circuit voltage, we need to redraw the circuit again, where we will be replacing this 9 ohm resistance by an open circuit. Let's say this is terminal A, this is B. It's 20 volt source, 4 ohm resistance, 6 ohm resistance. Load resistance is now removed from the circuit. Let's mark the polarity of open circuit voltage like this. Current through this resistance was earlier Ix. Since the circuit is different from the previous one, the current is now different from Ix. Let's say it is Ix1. So that Ix1 will be reflected over here as 6 times Ix1. You need to notice that here the voltage supplied by this source was 6 times Ix. Since Ix, which is a controlling quantity, it has now different values, so that should be reflected over here. So I'm writing this one as 6Ix1. Now we need to find out this VOC. Now if we just look at these two terminals, these are same as the terminals of 6 ohm resistance. So if we find out that what is the voltage across the 6 ohm resistance, that is actually open circuit voltage. So VOC is actually voltage across 6 ohm resistance, and voltage across 6 ohm resistance is actually 6 into Ix1. So if we find out the value of Ix1, then we can have the value of open circuit voltage. Now the current through this loop is 0. Since it's an open loop, we don't need to assign the current to this. We need to assign current to this loop only, and that we can say as Ix1, because Ix1 is the current through 6 ohm resistance. Same current will flow through this 20 volt 4 ohm and through this 6 times Ix1 voltage source. Now if we apply KVL starting from this 20 volt source minus 20, then drop across 4 ohm resistance 4 Ix1, then drop across 6 ohm not drop across 6 ohm. It's a voltage source first, as negative sign is coming first, minus 6 times ix1. Then we have drop across 6 ohm resistance. I have marked the polarity of voltage drop as per the direction of ix1. So plus 6 ix1 equal to 0. These two terms are cancelling out each other, and ix1 is clearly 5 amperes, which will give us the value of VOC as 6 times ix1 is 30 volts. So open circuit voltage is 30 volts. Now the second step over here, after finding out open circuit voltage, is to calculate the short circuit current. Now when we try to calculate short circuit current, we need to redraw the circuit again. The load resistance terminals, now they should be replaced by short circuit. Let's draw the circuit again. We have 4 ohm resistance in series with 20 volt source, and here we have a dependent source, 6 ohm resistance. These are the load terminals which we need to replace by short circuit, and we will be calculating the current over here, A and B. Now this short circuit is in parallel with 6 ohm resistance. Since it's in parallel with 6 ohm resistance, whole of the current will flow through the short circuit only. When whole the current will flow through short circuit, then this Ix value is 0. Ix is 0. Why? Since all current will flow through short circuit, that is between terminal A and B through this path. This is a short circuit path. So basically the 6 ohm is actually short circuited. Ix is 0. When Ix is 0, then the voltage supplied by this source is also 0. So this circuit will actually get simplified to a 4 ohm resistance, 20 volt source. We don't have the source anymore. We don't have 6 ohm resistance anymore in the circuit. Here we have A and B, through which the current is ISC. So ISC is actually 20 by 4, simply 5 ampere. So this is how we calculate the current. Now the thing which we need to understand over here, that how this source is getting eliminated. The calculation is quite easy. It's simple voltage source in series with a single resistance. It's not difficult to calculate this 5 ampere source. We need to understand that how we reach to this simplified circuit from this one. This is because 6 ohm resistance is in parallel with short circuit. The controlling quantity, that is Ix, that was flowing through 6 ohm. In parallel with 6 ohm we have short circuit. Since the current has property that it follows the minimum resistance path, so whole current will flow through this short circuit between terminals A and B. Through this 6 ohm the current Ix is actually 0. When this is 0, then the voltage supplied by this is also 0. That's why this source is no more there in the circuit. We have a simplified circuit. I hope it's clear that how we got this ISC as 5 ampere. So once we have the value of open circuit voltage and short circuit current, then we can calculate RTH as ratio of open circuit voltage to short circuit current. Open circuit voltage was 30, short circuit current is 5 ampere. So RTH is 6 ohm. Question was to find out the current through load resistance, that is 9 ohm resistance, using Thevenin's theorem. So we need to draw its Thevenin equivalent. 30 volt in series with Thevenin resistance, that is 6 ohm. A, B, in between we have to connect the load resistance back, that is 9 ohm. So I 9 ohm is 30 upon 9 plus 6, which will give answer as 2 ampere. Now moving on to next problem. Problem is determine the current in 16 ohm resistor using Thevenin's as well as Norton's theorem, or you can use any one. So basically once we have the value of open circuit voltage and short circuit current, we can draw both the equivalents. There is no issue. Now the circuit for this problem is, we have a 40-volt source in series with 10 ohm resistance, and here in this branch we have a dependent source 0.8 Ix, 6 ohm resistance, then 16 ohm. Current through the 16 ohm resistance is Ix. So basically these terminals, if this is A and this one is B, these are the load terminals. Again, due to presence of this current dependent current source, we can't find out the value of RTH directly. We need to find out the value of open circuit voltage as well as short circuit current to obtain RTH. So first step is for VOC. For VOC, draw the circuit again, and always draw the circuit again. Never try to calculate from the circuit which is given in the question only. Draw the circuit again as per the modification. Now what is the modification over here? We need to remove the load resistance. So when the load resistance is removed, the 60 ohm resistance is no more there in the circuit. So the current Ix which was flowing from A to B, that is actually 0 in this case because these terminals are now open. When Ix is 0, so this point Ix is actually also 0. When this one is 0, it means we don't have this current source in the circuit. So this circuit is now modified, or we can say simplified, to the circuit 10 ohm, 6 ohm, and here we have A and B. Since the A and B terminals are open, the current through 6 ohm and the 10 ohm series combination is 0. So if we try to measure that what is the voltage between these two, that is same as the voltage source. So if this terminal is positive, the B is negative, then VOC is 40 volts. Directly, we don't need to do any calculation. It's clear from the circuit only. There is no drop across 10 ohm, there is no drop across 6 ohm. All the voltage which is supplied by this voltage source, that is appear across terminals A and B, and we are getting the value of VOC as 40 volts. Now the second step is for ISC. Now we have to calculate the short circuit current. So when we have to calculate the short circuit current, we need to draw the circuit again. 10 ohm resistance, 40 volt source, and here we have current source, 6 ohm resistance, A, B, terminals, they should be short circuited. Through this current is ISC, which is same as IX, because IX is the current through A and B. This is 0.8 IX. Now we need to find out the value of ISC. How can we find out ISC? We can find out by mesh analysis, or we can find it out by node analysis. If we try to find it out by mesh analysis, I1, I2, we have to assign two currents. I2 and ISC basically both are same. So that will be a case of super mesh, since this 0.8 IX is a current source common between two meshes. So instead of going with that method, I would prefer to go with the nodal analysis, considering this one as reference and this one is a node at voltage V. Now if I have the value of V, then I can calculate the value of ISC as V upon 6. V minus 0 by 6 is the current, which is same as IX. So I need to write just one equation for this node, and second equation is the equation of controlling quantity in terms of node voltage that I had already written, that Ix, or short circuit current, that is equal to V by 6. Now when we apply KCL at this node, then current through this 10 ohm resistance is V minus 40 by 10. Current in this branch is 0.8 Ix. Current in this branch is V by 6, and this should be equal to 0. Now in this equation we can substitute the value of Ix, 0.8 V by 6 plus V by 6 equal to 0. So the solution of this equation will give us the value of V as 10 volts. So when V is 10 volts, then ISC is V by 6, 10 by 6, which comes out to be 1.667 ampere. So now we got the value of short circuit current, we have the value of open circuit voltage as well. We can calculate RTH or RN, both are same, VOC upon ISC. VOC was 40, ISC 1.667 amperes. So RTH is actually 24 ohms. Now we can draw both the Thevenin as well as Norton's equivalent. When we draw Thevenin's equivalent, we have to draw a voltage source in series with Thevenin resistance. Then here we will have between A and B the load resistance, that is 16 ohm. If we want to find out the current through 16 ohm, then I 16 ohm will be 40.24 plus 16, that is 1 ampere. We can draw the Norton's equivalent as well. In Norton's equivalent, we draw the current source, which is given as short circuit current in parallel with Norton resistance, 24 ohm, and between A and B, we have to connect the load resistance back, that is 16 ohm. The value of short circuit current was 1.667 amperes. In order to find out the current through 16 ohm, we have to apply current division rule. Now current division rule is source current into opposite branch resistance divided by opposite branch resistance plus resistance of the branch through which we are finding out the current. Again, we get the answer of I16 ohm as 1 ampere. So whether you are going with the Thevenin's theorem or by Norton's theorem, the answer is remaining same. There is no change. So this one is Thevenin's equivalent, where we have replaced the complicated circuit by a single voltage source in series with single resistance, and this one is Norton's equivalent, in which we have replaced the complicated circuit by a single volt current source in parallel with single resistance. Now the last problem which I am considering over here is find the current in 2 ohm resistor for the network shown below using Thevenin's theorem, or same can be replaced by Norton's as well. There is no difference because we are already calculating short circuit current and open circuit voltage in this case, since we are going to have a dependent source. Now the circuit looks like this. We have one independent voltage source, one independent current source, one dependent current source, this current source is supplying current 2 times Ix, where Ix is the current through this 1 ohm resistance. And this 2 ohm resistance is actually load resistance. Now, for Thevenin's equivalent, we need open circuit voltage and RTH. And to find out RTH, we need the value of short circuit current as well. That's why I said that we can draw the Thevenin as well as Norton's equivalent, though it's asked to calculate by Thevenin's theorem only. Now, for obtaining VOC, let me draw the circuit again. One ampere source in parallel with 3 ohm resistance, and here we have 2Ix current source, and the load terminals should be replaced by open circuit. In order to find out VOC, we had removed the load resistance. Let's mark this terminal as positive, this one is negative, and here we have voltage VOC. Now we have a current source over here which is controlled by current through this 1 ohm resistance. Since these terminals are open, this current is not flowing anywhere and the drop voltage across this will not affect the open circuit voltage. So whatever the voltage is there across this 3 ohm resistance, same is the voltage across this open circuit. So VOC is equals to voltage across the 3 ohm resistance. And in order to find out that what is the voltage through this 3 ohm resistance, we need to find out the current through 3 ohm. For that, let's mark this current as I1, this current is I2. Now this is the case of super mesh where we need to combine mesh 1 and 2. When we combine mesh 1 and 2, minus 10 plus 1 to I1 plus 3 into I2 equal to 0. So this will give the equation as I1 plus 3I2 equal to 10, first equation. Second equation will be a constraint equation. Now the constraint equation is I2 minus I1 equal to 1. This is the second equation. Now when we solve these two equations, and we can have the value of I2 as 2.75 ampere and I1 will be 1.75 ampere. We need the value of I2 in order to calculate VOC, because VOC is voltage across 3 ohm resistance, 3 into I2. So it's 3 into 2.75, 8.25 volts. So this is the value of open circuit voltage. Next step is we need to calculate short circuit current through the load term. Next step is to calculate short circuit current. For calculating short circuit current, we have to redraw the circuit again. For ISC, we have to replace the load terminals by short circuit. Here we have 10 ohm resistance in series with, 10 volt source in series with 1 ohm resistance, followed by 1 ampere current source which is connected in parallel with 3 ohm resistance, and here we have the dependent source, and the load terminals, they are to be replaced by short circuit. Current supplied by this current dependent current source is Ix, 2 times Ix, where Ix is the current through 1 ohm resistance. Now this circuit, this one is different from the initially given circuit. What was there in case of initial circuit? We had 2 ohm resistance. When this resistance was there at that time, current through 1 ohm resistance was Ix. Since the configuration is different, let's write this current as Ix1, and that will be reflected over here as 2 times Ix1. Now we need to find out the short circuit current. In order to find short circuit current, we can assign 3 different mesh currents: I1, I2 and I3. Now in this case, we could have gone with the nodal analysis as well. It's our choice that which we want to solve. If we want to go with nodal analysis, then we will have just one equation, one node and second node. These two are at same potential. So you will have just one nodal equation. This will be the reference. So when we have, and if we try to solve it with mesh analysis, then we have 3 different meshes. From the outer mesh, we will have the value of I3 as 2 times Ix1. Then the value of mesh 1 and 2, they should be combined together to make a super mesh. So in this problem, it's very clear that which method is beneficial. If we go with mesh analysis, then it will become a lengthy problem in comparison to the case when we have the use of nodal analysis. So I will solve it with nodal analysis. The current in this branch is Ix1, and that is flowing towards the node Ix1. Then 1 ampere is also flowing towards the node. Again, it's an incoming current. Current through 3 ohm resistance, we don't know the direction. So let's mark that this is outgoing current, and this 2 times Ix2 is also an outgoing current. So this should be equal to 2 times Ix2 plus current through 3 ohm as V by 3. Now we need to find out Ix2. One thing we can write, so not Ix2, it's Ix1. We can write this Ix1, it's flowing from reference towards node 1. So it will be 0 minus minus of 10 minus V by 1. So Ix1 is basically 10 minus V. From here we can write V equal to 10 minus Ix1. Now when we use this value of V in this equation, we have Ix1 plus 1 equal to 2 times Ix1 plus 10 minus Ix1 upon 3. So this will give us the equation as 3 times Ix1 plus 1 equal to 6 times Ix plus 10 minus Ix1. 3 times Ix1 plus 3 equal to 5 Ix1 plus 10, which will give us a value of Ix1 as minus 7 by 2 ampere. Now once we have the value of Ix1, then we can have the value of short circuit current as well, since short circuit current is 2 times Ix1. So Isc is 2 times Ix1, and that is minus 7 amperes. We got the value of VOC as 8.25. Now we have the value of Isc as minus 7. So RTH, which is same as R Norton, is ratio of VOC upon Isc. VOC is 8.25, Isc is minus 7. So resistance is actually minus 1.178 ohm. So this negative resistance over here, that indicates that it's a negative resistance region, and 2ix current source is actually representing a semiconductor device. You can't take the magnitude of this Isc only, because what we have taken when we have considered the voltage polarity, this terminal was positive, this one was negative, and as per this polarity the current should flow in the downward direction only. If the current is not flowing in downward direction, that's why this one is coming as minus 7. So we can't just ignore this, we have to take it as it is in the calculation of R Thevenin and R Norton, and this negative sign indicates a negative resistance region. Now question was, we have to find out the current through the load resistance using Thevenin's theorem. So the Thevenin equivalent is 8.25 volts in series with the resistance, and here we have to connect the load resistance, that is the 2 ohm resistance, and we need to find out I2 ohm. So I2 ohm is 8.25 upon minus 1.178 plus 2, that is 10.07 ampere. So what we can see over here, that the current is actually more than the voltage, that indicates a negative resistance region. Similarly, you can also draw the Norton's equivalent as well. So till now I had taken two different Till now, I had considered 6 different problems in 2 different videos for obtaining the Thevenin and Norton's equivalent when we have dependent as well as independent sources present in the network. We can have the special case as well when we don't have any independent source present in the network, but we have a dependent source. How to solve that type of problems, that I will consider in the next video. I hope all these problems will help you out in understanding the Thevenin and Norton's theorem. I thank you all for watching this video, and if you find the video useful to you, please consider subscribing the channel.